What if the most profound secrets of our universe aren't hidden in some distant nebula, but lie right at the heart of what we thought we already knew? What if the very fabric of our reality, the vast, expanding cosmos you inhabit, is not a beginning in itself, but a continuation? A cosmic offspring born from something unimaginably enormous, something we've spent decades trying to comprehend. A black hole. Pause for a moment. Feel the weight of that question. It isn't just a flight of fancy. It's a journey into the deepest, most mind-bending corners of physics, a detective story where the clues are written in the language of space-time itself. And the two most astonishing crime scenes in this cosmic investigation, the ones that share the most unsettlingly similar fingerprints, are the beginning of everything and the end of everything. Welcome to Celestial Enigmas. Today we're embarking on a quest to connect the two most extreme phenomena known to science: the Big Bang, the explosive birth of our universe, and the black hole, the ultimate gravitational trap. We'll explore a radical, yet elegant hypothesis that suggests these two cosmic titans aren't just similar, but fundamentally linked. What if our entire universe is a black hole, nested within another larger universe? And what if the very evidence for this astonishing claim has been staring us in the face, hidden in plain sight, within the equations of Albert Einstein? For generations, humanity has looked up at the stars and asked, where did we come from? The prevailing scientific answer for nearly a century has been the Big Bang. Imagine, if you can, a moment, roughly 13.8 billion years ago, when all the matter, all the energy, all the space-time of our observable universe was compressed into an infinitely dense, infinitely hot point, a singularity. From this impossible point, everything you see, everything you are, began to expand, cool, and evolve. It's a story of creation on the grandest scale, a cosmic dawn of unimaginable power. Now, shift your gaze to the opposite extreme, the black hole. You've heard the name, you've seen the images, perhaps you even grasp the terrifying concept. These are regions of space-time where gravity is so intense that nothing, not even light, can escape once it crosses a boundary known as the event horizon. At the heart of every black hole, according to classical general relativity, lies another singularity, a point of infinite density, where all the mass of the collapsed star is crushed into an infinitesimally small volume, and where the laws of physics, as we understand them, break down. Do you see the unsettling parallel? Both concepts, the Big Bang and the black hole, invoke a singularity, a point of infinite density and curvature, a place where our physics equations throw up their hands in despair. For a long time, physicists viewed these singularities as problematic, as mathematical imperfections in Einstein's otherwise elegant theory of general relativity. They were like cosmic walls, beyond which our understanding simply ceased. But what if these problems aren't flaws at all? What if they are clues? What if these two seemingly unrelated cosmic behemoths, the universe's beginning and a star's ultimate demise, are actually two sides of the same astonishing coin? Let's become cosmic detectives for a moment. Imagine two separate crime scenes. One, the Big Bang, is a scene of explosive creation, light, and expansion. The other, a black hole, is a scene of implosive destruction, darkness, and collapse. They seem diametrically opposed, don't they? But then you notice something peculiar. Both scenes bear the exact same impossible fingerprint, the singularity. To truly grasp this, we need to understand the language of gravity itself. Albert Einstein's general relativity. Published in 1915, this revolutionary theory reshaped our understanding of the cosmos. Einstein showed us that gravity isn't some invisible force pulling objects together. It's the warping and curving of spacetime itself by mass and energy. Think of a bowling ball placed on a stretched rubber sheet. It creates a dip, and marbles rolling nearby will curve towards it. That dip, that curve, is gravity, and it is within these elegant equations that we find the first, most striking piece of evidence for our cosmic detective story. Consider the Schwarzchild radius. This isn't just a theoretical concept. It's a precise mathematical boundary defined by Carl Schwarzchild in 1916, just a year after Einstein published his theory. He found the first exact solution to Einstein's field equations for a spherical, non-rotating mass. The Schwarzchild radius is the point of no return for any mass, the distance from a gravitating object at which light can no longer escape. Any object compressed within its own Schwarzchild radius becomes a black hole. Its formula is deceptively simple: R stereo 2gm C2, where G is the gravitational constant, m is the mass, and c is the speed of light. It tells us that for any given mass, there is a specific radius at which it becomes a black hole. Now let's turn our attention to the universe itself. Our cosmos is expanding, and that expansion can be characterized by something called the Hubble radius, or the observable universe's radius. This is the distance light has been able to travel to us since the Big Bang, essentially defining the edge of what we can currently see. Our best measurements tell us that the observable universe is roughly 13.8 billion light-years in radius. Here's where the cosmic detective story takes an astonishing turn. What if we were to take the estimated total mass of our observable universe, a truly staggering 1.5 × 10⁻53 kilograms, and plug it into Schwarzschild's equation? What would the calculated Schwarzschild radius be for an object with the mass of our entire universe? The answer, astonishingly, is approximately 13.8 billion light-years. Let that sink in for a moment. The calculated Schwarzschild radius for an object with the mass of our entire observable universe is almost precisely the measured radius of our observable universe. It's a numerical coincidence that has baffled and intrigued physicists for decades, first formally noted by researchers like Raj Pathria in the 1970s. This is our first dramatic aha moment, brought to life with a stunning 3D visualization. Imagine side by side two identical spheres. On the left, you see our universe expanding from a central point, its edge pushing outward, mapping the 13.8 billion light-year reach of the Hubble radius. On the right, you see a black hole, its mass collapsing inward, its event horizon settling precisely at 13.8 billion light-years, defined by the Schwarzschild radius. The two spheres, one expanding, one collapsing, meet at the same boundary, the same mathematical fingerprint. Is this merely a bizarre cosmic coincidence, a quirk of numbers that holds no deeper meaning? Or is it a profound clue, hinting at a hidden connection between the very beginning of our reality and the ultimate cosmic devourer? This is not to say our universe is a black hole in the traditional sense you might imagine, a compact, super-dense object with immense tidal forces that would rip you apart. Far from it. From our perspective inside, the universe appears vast, expanding, and on large scales, remarkably flat. We don't feel like we're being crushed by immense gravity. This is because the gravitational forces within such an enormous cosmic black hole would be incredibly uniform across the vast scales we observe. The average density required for a black hole, the size of our universe to exist, is surprisingly low. About 9.9 × 10⁻27 kilograms per cubic meter, roughly 6 hydrogen atoms per cubic meter. This isn't the crushing density you associate with stellar black holes. It's precisely the critical density our universe is observed to have, which gives it its flat geometry, this mathematical mirror. This uncanny numerical alignment suggests that the equations governing the Big Bang and the equations governing a black hole's boundary might be describing fundamentally the same phenomenon, just viewed from different perspectives. From the outside, you might see a black hole. From the inside, however, you might experience an expanding universe. This perspective shifts the cosmic detective story dramatically. The singularity, that problematic, infinitely dense point at the heart of both the Big Bang and a black hole, might not be a wall, but a doorway. What if the matter that collapses into a black hole in a parent universe doesn't just vanish into nothingness, but rather bounces back, expanding into a new universe on the other side of the event horizon? This is the core insight of modern proponents of this theory, like physicist Nikodem Popowski, who suggests that a property of spacetime called torsion could prevent true singularities, allowing for a cosmic rebound. Imagine a seed. It's tiny, compact, holding within it the blueprint for an entire tree. It falls to the ground, seemingly disappearing into the soil, only to sprout forth, pushing out new branches, new leaves, creating a whole new organism. In this powerful organic analogy, our universe is that seed, sprouting from a cosmic parent. The black hole in the parent universe isn't a destroyer, but a cosmic womb, a birthing canal for new realities. The moment of collapse in the parent universe becomes the Big Bang for its offspring. This is a universe that reproduces, a cosmos that gives birth, and the profound implications ripple through every aspect of our existence. The terrifying singularity is no longer an unknowable void, but a point of cosmic genesis. The Big Bang isn't an arbitrary explosion, but a physical process, a natural outcome of the laws of physics operating on a grander multiversal scale. So, the central question of our cosmic detective story emerges. Is this striking similarity between the mathematical descriptions, the critical densities, and the very structure of the Big Bang and a black hole a mere quirk of numbers? Or is it a fundamental clue, perhaps the most profound hint yet, that our universe is a black hole, nested within another, larger universe, a cosmic seed continually sprouting new realities? The journey to uncover the answer has just begun, and the universe's true nature might be far more interconnected and far more alive than we ever dared to imagine. The universe's true nature might be far more interconnected and far more alive than we ever dared to imagine. But to truly grasp this audacious hypothesis, this idea that our entire cosmos could be a seed sprouting from the heart of a black hole, we must first understand the bedrock upon which it stands. We must journey back to the mind that redefined reality itself, to the equations that weave the very fabric of existence, Albert Einstein's general theory of relativity. For centuries, gravity was a familiar if mysterious force. Isaac Newton described it as an invisible pull, a distant hand reaching across the void to tug apples from trees and hold planets in orbit. It was elegant, predictive, and it worked. Yet there was always an unspoken question. How did this force know to act? How did the Earth know the Sun was there, across 93 million miles of empty space, to pull it into its graceful dance? Newton gave us the what of gravity, but not the how. Then, in 1915, Einstein shattered that comfortable understanding. He didn't just tweak Newton's theory, he overturned it completely, offering a vision so profound, so utterly counterintuitive, that it still challenges our imagination today. Einstein didn't see gravity as a force at all. He saw it as a deception, a cosmic illusion. What we perceive as gravity, he revealed, is simply the effect of massive objects warping the very stage upon which the cosmic drama unfolds, space and time. Imagine, if you will, the universe not as an empty, static container, but as a vast, invisible trampoline, stretched taut across infinity. This isn't just a simple analogy. It's a profound conceptual leap. This trampoline is what physicists call spacetime, a four-dimensional fabric where three dimensions are space, up, down, left, right, forward, back, and the fourth, inextricably linked, is time. Now picture this trampoline in your mind. When there's nothing on it, it's perfectly flat, perfectly smooth. A marble rolled across it would travel in a straight line, unimpeded. This is how light travels through empty space, and how objects would move if there were no gravity. But what happens when you place something heavy on that trampoline? Let's put a bowling ball, representing a star like our sun, right in the center. What does it do? It creates a gentle dip, a subtle curve in the fabric. This isn't a force pulling on the trampoline. It's the mass itself deforming the trampoline. Now, roll a smaller marble, representing a planet like Earth, near this dip. What happens? The marble doesn't travel in a straight line anymore. It curves inward, rolling around the bowling ball, caught in the depression of the fabric. This, Einstein declared, is gravity. The Earth isn't being pulled by a mysterious force from the Sun. Instead, the Sun's immense mass has curved the space-time around it, and the Earth is simply following the shortest, straightest path available to it through that curved reality. Its straight path is an orbit, because the space it's moving through is no longer flat. It's like walking in a perfectly straight line on the surface of the Earth. You eventually come back to where you started, not because a force pulled you, but because the surface itself is curved. Every object in the universe, from the smallest atom to the grandest galaxy, leaves its imprint on this cosmic fabric, shaping it, bending it, giving it form. And in turn, the shape of that fabric dictates how everything else moves. Space tells matter how to move, and matter tells space how to curve. It's an elegant, self-referential dance, a beautifully intricate ballet, choreographed by the universe itself. But what happens when the mass isn't just heavy, but inconceivably, unimaginably dense? What happens when you don't just place a bowling ball on the trampoline, but an object so incredibly heavy, so infinitesimally small, that it doesn't just create a gentle dip? This is where the story takes a truly mind-bending turn. A black hole isn't just a bigger, deeper dent in the trampoline. It's something far more extreme, far more violent. Imagine taking that bowling ball, but then crushing it down to the size of a pea, and then crushing it even further, to the size of an atom, and then further still, until its entire mass is concentrated into an infinitely small point, a singularity. At this point, the trampoline analogy needs a dramatic upgrade. The fabric of space-time isn't just curved anymore. It's torn. It's ripped open, creating not a gentle slope, but a bottomless well, a cosmic vortex. If our universe is a trampoline, then a black hole is a point where the fabric has been pierced, where reality itself plunges inward like a perpetual waterfall. Think of it this way. The space and time around a black hole are not just slightly bent. They are utterly contorted, collapsing inward on themselves with such ferocity that there is no escape. It's as if a river flowing gently suddenly hits a point where the current becomes so strong, so relentless, that nothing, not even a speedboat at full throttle, can make headway against it. Everything is dragged downstream, inexorably, irresistibly. This leads us to the most iconic and perhaps most misunderstood feature of a black hole: its event horizon. This isn't a solid surface you could stand on, nor is it a tangible boundary painted in the cosmos. The event horizon is a point of no return, a conceptual boundary in spacetime. But what defines it? What makes it so absolute? The brilliant German physicist Karl Schwarzchild, in 1916, just a year after Einstein published General Relativity, found the very first exact solution to Einstein's equations for a spherical, non-rotating mass. His calculations revealed a critical radius, a sphere around any mass within which something truly extraordinary occurs. This radius, now famously known as the Schwarzchild radius, defines the event horizon. And here is the aha moment, the profound realization that fundamentally alters our understanding of reality. At the event horizon, the curvature of spacetime becomes so extreme that spacetime itself is falling inward faster than the speed of light. Let that sink in for a moment. It's not just that light can't escape. It's that the space in which the light is traveling is being pulled inward at a speed exceeding light's own escape velocity. Imagine you're on a treadmill. If the treadmill is moving slowly, you can easily walk or run against its motion and make progress. But what if the treadmill speeds up to, say, 100 miles per hour? Even if you run as fast as you can in the opposite direction, you're still being carried backward because the very ground beneath your feet is moving faster than you are. The event horizon is precisely this, but on a cosmic scale, and with spacetime as the treadmill. No matter how fast you travel, no matter what direction you point your spaceship, if you cross that invisible line, you are irrevocably being carried toward the singularity at the center. You are caught in the current of reality's waterfall, and there is no coming back. Everything, every particle of matter, every photon of light, every ripple of information is swept into the abyss. This isn't just a powerful metaphor. It's the literal description of what Einstein's equations tell us. The geometry of spacetime itself is so dramatically warped that all paths, no matter how they begin, eventually lead inward. Time and space swap roles. Inside the event horizon, what we perceive as time becomes like a spatial dimension, an unavoidable direction you are forced to travel in. And what we perceive as space becomes more like a temporal dimension, something you can't travel back and forth in. The future is the singularity, and you are always constantly moving towards it. Now, you might be thinking, if our universe were truly inside a black hole, wouldn't we feel it? Wouldn't the immense gravitational forces tear us apart? This is a crucial question, and it highlights a common misconception about black holes. While a small black hole, formed from a collapsing star, would indeed have incredibly strong tidal forces that would spaghettify you long before you reached the event horizon, a supermassive black hole, or one on the scale of an entire universe, behaves very differently. For a black hole with a sufficiently large mass, the event horizon itself can be incredibly vast. Imagine one with a radius of billions of light years. If you were to cross the event horizon of such a colossal black hole, you wouldn't feel anything dramatic at that precise moment. The curvature of spacetime would be so uniform across your body, and even across our solar system, that you wouldn't experience any noticeable tidal forces. You would simply continue onward, unaware that you had just passed the ultimate point of no return. You would still see stars, still experience space as vast and expanding, but you would be irrevocably falling into a future that leads only inward. This is a critical insight. Our everyday experience of gravity is of local, varying forces, but within a truly enormous black hole, the gravitational pull across vast cosmic distances would be remarkably uniform. From our perspective inside, the universe would still appear to be expanding in all directions, just as our cosmological observations confirm. The fall would be a global, pervasive experience, not a localized, crushing force. This profound understanding of gravity as the geometry of spacetime and black holes as its most extreme manifestation, is the foundation for our cosmic detective story. Einstein's equations aren't just describing a force, they are describing the very architecture of reality, the rules by which universes might be born. The universe's grand design isn't a flat, empty stage, but a dynamic, ever-curving fabric, constantly being reshaped by the matter and energy within it. And at its most extreme, this curvature creates the ultimate cosmic traps, the black holes, where spacetime itself flows like an unstoppable river. The stage is now set. We have explored the fundamental principles of general relativity, the invisible trampoline of spacetime, and the terrifying, beautiful reality of a black hole's event horizon. That point where the very fabric of existence cascades inward, faster than light. But what if the Big Bang, the explosive birth of our entire cosmos, wasn't just like the formation of a black hole, but was the formation of a black hole? What if the universe we inhabit, the galaxies we observe, the stars we gaze upon, are all contained within this cosmic waterfall? The implications are staggering. If gravity is truly the sculptor of reality, and if black holes are gravity's ultimate masterpiece of curvature, could it be that our entire observable universe is nothing more than the inside of one of these cosmic behemoths, hidden from an external observer in a parent universe? Could the Big Bang have been the moment this new universe sprang into being, not from an arbitrary explosion, but from the elegant, inevitable physics of a black hole's collapse? This is where the detective work truly begins. With Einstein's equations as our guide, we can now look for the uncanny similarities, the mathematical mirror images that connect the vast, expanding cosmos we call home to the enigmatic, all-consuming maw of a black hole. Because if the universe is indeed a black hole, the evidence isn't hidden in some distant nebula. It's woven into the very fabric of our reality, waiting to be uncovered by the language of physics. The next clue lies in the startling numerical coincidences that bridge these two cosmic titans. The universe, in its boundless expanse, often presents us with illusions. We perceive it as vast, empty, and indifferent. Yet, beneath the surface of that perception, the universe whispers its secrets in the language of mathematics. And sometimes, those whispers reveal a truth so profound, so utterly counterintuitive, that it forces us to reconsider everything we thought we knew about our cosmic home. You see, for all the complexity that Einstein's equations reveal about the fabric of spacetime, there's a startling simplicity at their heart, a fundamental truth that governs everything from a falling apple to the spiraling dance of galaxies. And when we apply this fundamental truth to the largest structures we know, our very own universe and those enigmatic black holes, a truly astonishing pattern emerges. A pattern so precise, so numerically perfect, that it makes you wonder if it's merely coincidence, or if it's the universe's way of revealing its deepest identity. Imagine for a moment that we are cosmic detectives, and our universe is a subject undergoing a profound, almost intimate examination. We're not looking for fingerprints or eyewitness accounts. Instead, we're performing a kind of cosmic DNA test. We're scrutinizing the genetic code of our cosmos, its fundamental properties, to see if they match the profile of something else entirely. What if, upon analyzing the core data of our universe, the results came back with a perfect, undeniable match to the genetic profile of a black hole? That's the stunning hypothesis we're about to explore, one that sends a shiver down the spine of scientific intuition. At the heart of this cosmic DNA test lies an equation so elegant, yet so powerful, that it defines the very boundary of a black hole. It's called the Schwarzchild radius equation, named after Carl Schwarzchild, who, in the aftermath of Einstein's groundbreaking general relativity, provided the very first exact solution to those field equations for a spherical mass. This equation, R2GMCY, is deceptively simple. It tells us the precise radius an object of a given mass, m, must shrink to, for its gravity to become so immense that nothing, not even light, can escape its grasp. Here, g is Newton's gravitational constant, and ct is the speed of light, fundamental constants of nature. Now, pause and truly consider what this equation represents. It's not just a mathematical formula, it's a cosmic threshold. It draws an invisible, yet absolute line in the sand of spacetime, marking the point of no return, the event horizon. Beyond this boundary, the familiar laws of physics, as we experience them, seem to unravel, and everything falls inexorably towards an unknown fate. This is the defining characteristic of a black hole, a region of space-time where gravity triumphs over all, sealing away whatever lies within. So, how does our universe measure up against this profound cosmic blueprint? Let's put the observable universe on the cosmic DNA scanner. What are its most fundamental genetic traits that we can quantify? Well, for starters, there's its immense mass. Through meticulous observation and calculation, physicists have estimated the total mass of the observable universe. That's all the stars, galaxies, dark matter, and dark energy within our cosmic horizon, to be an astonishing 1.5 x 10^53 kilograms. It's a number so vast it's almost incomprehensible, a testament to the sheer scale of existence. And what about its size? Our observable universe has a known radius, determined by the distance light has had time to travel to us since the Big Bang. Given its age of approximately 13.8 billion years, the radius of our observable universe is estimated to be about 13.8 billion light-years. This is the vast cosmic expanse we can, in principle, see and interact with. Now, for the aha moment, the stunning reveal of this cosmic DNA test. Imagine a dazzling data-driven animation unfolding before your eyes. On one side of the screen, we see the monumental figure representing the estimated mass of the observable universe, 1 x 10^33 kilograms. On the other side, the elegant yet intimidating Schwarzchild radius equation, R=2GMC2, glows with anticipation. We watch as the mass of our universe, 1.5 x 10^53 kilograms, is digitally plugged into the m in that equation. The constants g and c2 are already there, immutable. The calculation begins, numbers whirring, symbols cascading. There's a palpable sense of anticipation as the formula processes this immense cosmic input. And then, the result materializes on screen, stark and undeniable. The calculated Schwarzchild radius for an object with the mass of our observable universe is precisely 13.8 billion light-years. The animation then performs a breathtaking merge. The calculated number, 13.8 billion light-years, drifts across the screen, slowly aligning itself with another identical number, the independently measured radius of our observable universe. They click into place, perfectly superimposed. The two separate concepts, the theoretical boundary of a black hole and the empirical measurement of our cosmos, merge into one unified, astonishing truth. This isn't just a near miss. It's an exact, profound mathematical coincidence. The mass of our universe, when subjected to the very equation that defines a black hole's event horizon, yields a radius that is identical to its actual observed physical size. It's as if the universe is looking back at us from a mirror and its reflection is that of a black hole. This is the central piece of evidence that forms the bedrock of this mind-bending hypothesis. It suggests that our universe, by its very nature, perfectly fits the mathematical description of a black hole. But the coincidences don't stop there. This mathematical alignment leads to another profound implication concerning the density of our universe. When people hear black hole, they often conjure images of infinite density, a point of singularity so compact that it defies imagination. While many black holes do indeed crush matter to incredible densities, the critical density required for a black hole, the size of our entire observable universe, is surprisingly low. Our universe, as it happens, is very close to its critical density, a specific average density required for its geometry to be flat, neither curving inward like a sphere, nor outward like a saddle. This critical density is a staggeringly low figure, roughly 9.9 gigs 10 to 27 kilograms per cubic meter, which amounts to about 6 protons per cubic meter. It's almost unfathomably diffuse, far from the crushing densities we associate with stellar black holes. And here's the kicker. If you take a black hole with the mass of our observable universe and calculate its average density, if it were indeed a black hole with a radius of 13.8 billion light-years, you find that it, too, would possess this exact same critical density. This isn't just one numerical match. It's a double whammy of cosmic proportion. Our universe's mass and radius fit the Schwarzchild equation, and its overall average density matches the critical density for a black hole of that size. These aren't isolated facts. They are interconnected threads, weaving a consistent, albeit deeply unsettling tapestry. Now, a natural question arises, a very human one. If we are inside a black hole, why don't we feel it? Why aren't we being stretched into spaghetti by immense gravitational tides, as popular science often depicts? The answer lies in scale and uniformity. The gravitational forces within a black hole the size of our universe would be incredibly uniform across the vast distances we inhabit. Unlike a stellar black hole, where the gravitational pull is dramatically stronger closer to the singularity, within a universe-sized black hole, the forces would be distributed so evenly that you wouldn't experience any differential pull. From our perspective, gravity would appear to be pulling equally in all directions, which is precisely what we observe as the expansion of space. Every galaxy appears to be moving away from every other galaxy, not because there's a central point of pull, but because space itself is stretching, carrying everything along with it. This is perfectly consistent with our cosmological observations, a key strength of this hypothesis. We wouldn't perceive ourselves as falling into a void. Rather, we would experience the constant outward expansion that has defined our universe since the Big Bang. This remarkable mathematical congruence didn't just appear out of thin air. It's a concept that has quietly simmered in the background of cosmological thought for decades. As early as 1972, physicist Raj Pathria was among the first to publish a paper noting this startling numerical coincidence between our universe's size and its Schwarzchild radius. Later, in the 2010s, physicists like Nikodym Popławski took this idea further, proposing that matter collapsing into a black hole doesn't form an infinitely dense singularity, but instead bounces to create a new universe on the other side of the event horizon. Popławski's work, using a modified theory of gravity called Einstein cartan theory, suggests that the extreme torsion, a twisting property of spacetime, inside a black hole could prevent the singularity and instead facilitate the birth of a new cosmos. This isn't just an intellectual curiosity, it's a potential solution to some of the most stubborn puzzles in cosmology. For one, It offers a physical, rather than purely theoretical, explanation for the Big Bang itself, instead of an unexplainable singularity, an infinitely dense point from which everything sprang. The Big Bang could be re-envisioned as the bounce of a white hole, the theoretical time-reversed opposite of a black hole, occurring within a larger parent universe. This framework provides a natural physical mechanism for the birth of our cosmos, replacing an unknowable beginning with a process governed by the very laws of physics we seek to understand. Moreover, this hypothesis offers a compelling explanation for the universe's arrow of time. Why does time flow relentlessly forward from past to future, never reversing? Within this model, our universe's forward progression of time is intrinsically linked to the one-way direction of falling into a black hole in the parent universe. Just as an object inevitably falls inward, past an event horizon, so too does our universe expand, creating a cosmic narrative that moves inexorably forward. The very irreversibility of time, a deep cosmic mystery, finds a potential anchor in the one-way journey into a black hole. This convergence of numbers, this stunning mathematical identity, invites us to stretch our imaginations far beyond conventional boundaries. It hints that the universe isn't just a random collection of matter and energy, but potentially an offspring, a cosmic child born from the gravitational collapse of a parent cosmos. Einstein's equations, once seen merely as descriptions of gravity, could then be reinterpreted as a profound set of rules, a cosmic creation engine that allows universes to reproduce, to give birth to new realities through the crucible of black holes. This is why we frame this as a thought experiment, a compelling hypothesis that inspires rather than dictates. It's a fascinating possibility, one that some physicists propose with serious consideration, pushing the boundaries of what we deem imaginable. It's not yet mainstream science, and there are many questions yet to be answered, many observations yet to be made, that could either bolster or refute this audacious idea. But the elegance of the mathematical match, the sheer numerical precision, is a powerful whisper from the cosmos, a hint that our universe might hold a secret identity, a hidden nature far grander and more interconnected than we ever dared to dream. It suggests that our universe is not an isolated phenomenon, but potentially just one of many, each born from the collapse of matter in a preceding cosmos. This model falls under the broader umbrella of multiverse theories, but it is distinct. It's not the quantum mechanical many worlds interpretation, nor is it the vast landscape of string theory. This is a universe born from the elegant yet violent physics of gravity itself, a cycle of cosmic birth and rebirth. This mathematical ghost in the cosmic machine isn't merely a coincidence. It's a profound invitation. It beckons us to consider that the very fabric of our reality, the expansion we observe, the densities we measure, are all perfectly consistent with being contained within the event horizon of a black hole. But if our universe is indeed a black hole, what then does that imply about the Big Bang itself? What does it mean for the problematic singularity, the infinitely dense point that traditional cosmology struggles to explain? And if our universe was born from a black hole, what incredible cosmic process could have orchestrated such a magnificent birth? The numbers have spoken, revealing a perfect match. Now, the real work begins to understand what that match truly means for our cosmic origins. This mathematical ghost in the cosmic machine isn't merely a coincidence. It's a profound invitation. It beckons us to consider that the very fabric of our reality, the expansion we observe, the densities we measure, are all perfectly consistent with being contained within the event horizon of a black hole. But if our universe is indeed a black hole, what then does that imply about the Big Bang itself? What does it mean for the problematic singularity, the infinitely dense point that traditional cosmology struggles to explain? And if our universe was born from a black hole, what incredible cosmic process could have orchestrated such a magnificent birth? The numbers have spoken, revealing a perfect match. Now, the real work begins to understand what that match truly means for our cosmic origins. For decades, the Big Bang has been the cornerstone of our cosmic narrative. It tells us that our universe began from an unimaginably hot, dense point and has been expanding ever since. But that point, the singularity, is where our equations break down. It's a place where physics as we know it ceases to exist. A bit of a cosmic shrug. This isn't just a problem for the Big Bang. It's the same perplexing singularity at the heart of every black hole. When a massive star collapses, all its matter is crushed into an infinitely dense point. And could the answer to one singularity be the key to understanding the other? What if, instead of being a cosmic dead end, a singularity is actually a cosmic doorway? Imagine a grand cosmic tree standing tall in a vast ancient forest. This tree isn't made of wood and leaves, but of galaxies and nebulae, governed by laws of physics we can only begin to fathom. This is our parent universe, a cosmos possibly far older and grander than our own, perhaps even operating in dimensions beyond our perception. And for the most massive among them, their death is the ultimate collapse. They form black holes. In this metaphor, a dying star within the parent universe is like a ripe fruit on the cosmic tree. When it collapses, it doesn't just vanish into an abyss. It becomes a seed. Our Big Bang, in this incredible scenario, wasn't a creation from nothing, but the moment that seed sprouted, blossoming into a new, separate, and utterly inaccessible dimension, our own universe. This concept finds its most compelling articulation in the work of physicists like Nikodym Popławski. He and others propose that the traditional singularity might be an artifact of an incomplete understanding of gravity. What if, instead of an infinite crush, there's a fundamental repulsion at extremely high densities? Popławski's model, for instance, incorporates a concept called torsion into Einstein's equations. Torsion, a property of spacetime itself, acts like an anti-gravitational force at the smallest, most compressed scales. So, when matter collapses into a black hole, it doesn't reach infinite density. Instead, at a critical point, torsion kicks in, preventing the singularity and causing the matter to bounce outward. But where does it bounce to? It bounces into a new, expanding space-time, a new universe on the other side of the event horizon. This is the aha moment we've been building towards, a profound shift in perspective that redefines our cosmic birth. To truly grasp it, let's embark on an awe-inspiring animated journey, one that takes us beyond the limits of our familiar three dimensions. Imagine, if you will, a being, an entity, existing in that four-dimensional parent universe. Their reality is richer, more complex than ours. They perceive not just length, width, and height, but an additional spatial dimension flowing around and through everything. For them, a black hole isn't just a sphere in 3D space. It's a more intricate, higher-dimensional structure, perhaps a pulsating four-dimensional vortex. From their vantage point, this magnificent 4D being watches as a colossal star in their own cosmos, many times the mass of our sun, begins its final death throes. The star, a vibrant beacon for billions of years, starts to flicker. Its core, having exhausted its nuclear fuel, can no longer withstand the immense inward pull of its own gravity. The animation shows this collapse in mesmerizing detail. The star implodes, its outer layers shedding light into the vacuum, while its core shrinks relentlessly. As it crunches down past its Schwarzchild radius, it vanishes from their direct perception, forming a 3D black hole, a point of no return for anything in their three spatial dimensions. The camera, representing our perspective, now pushes through the event horizon. We are no longer observing from the parent universe. We are journeying into the heart of this cosmic seed. The familiar starry tapestry of the parent universe shrinks away, replaced by an inky blackness that grows denser, more oppressive. You feel the crushing weight of gravity, the space-time around you warping, contorting. The light from outside is stretched and red-shifted into oblivion. You are past the point of no return. As you plunge deeper, the black hole's interior is not empty. It's a maelstrom of incredibly compressed matter, a super-dense plasma. The gravity is unimaginable. But then, something shifts. The pressure, instead of reaching infinity, plateaus. The torsion that Popowski speaks of, the intrinsic spin of space-time, begins to exert its repulsive force. The inward crush isn't absolute. Instead, the compression reaches its maximum. And then, with an astonishing release, it bounces. Visually, we now see the familiar imagery of our own universe's birth. The initial superhot plasma, the rapid inflation, the cooling and expansion that leads to the formation of fundamental particles, then atoms, then stars, and galaxies. It's our universe, recognizable and vast, but now with a profound new origin story. We see our universe's birth not as a creation from nothing, but as a physical transition, a process born from the collapse of matter in a preceding cosmos. The cosmic seed has sprouted. This model, while still speculative, elegantly addresses several profound puzzles. First, it sidesteps the problematic singularity of the Big Bang, replacing it with a physical bounce that our equations can actually describe. It grounds the beginning of our universe in known physics, albeit pushed to extreme limits, rather than a mysterious, unknowable void. It suggests that Einstein's field equations are not just descriptions of gravity, but a kind of creation engine, a set of rules that could allow universes to reproduce through black holes. This turns physics into a cosmic biology, where universes can have offspring. Secondly, it offers a tantalizing solution to the black hole information paradox. For decades, physicists have grappled with the question of what happens to the information of matter that falls into a black hole. Is it truly destroyed? This theory suggests no. The information isn't lost, it's preserved, not within the parent universe, but as the genetic code for the new universe inside. The unique properties of the matter that falls into the black hole could slightly influence the initial conditions and physical constants of the new universe that forms within it. This is a truly profound idea, that our universe isn't just a random occurrence, but potentially carries the imprints, the echoes of its parent. Our Big Bang, this cataclysmic event that birthed everything we know, might simply be the universe-sized equivalent of a star collapsing in a cosmos beyond our reach. We are living inside a cosmic seed that has germinated, expanding outward, completely oblivious to the parent tree from which it sprang. And from the perspective of that 4D being in the parent universe, our entire existence, all 13.8 billion years of our cosmic history, plays out inside a black hole they observe. Our entire universe, with all its galaxies, stars, and life, is contained within the event horizon of a black hole in a grander, older cosmos. This fascinating possibility transforms our understanding of cosmic origins from a singular, isolated event into a continuous generative process. It suggests a cyclical, self-propagating cosmos, where death in one universe leads to birth in another. It's a vision of an infinite cosmic ecology, a multiverse not of parallel realities, but of nested, interconnected universes, each one potentially a black hole to the next. Of course, this remains a hypothesis, a brilliant thought experiment that stretches the very limits of our scientific imagination. Mainstream cosmology continues to explore other avenues for understanding the Big Bang and the nature of singularities. The concept of torsion, while present in some modified theories of gravity, is not universally accepted, and direct observational evidence for a parent universe remains by definition elusive. How could we ever look outside our own universe to confirm such a radical idea? Yet, the elegance of the solution, the way it resolves some of the deepest conundrums in physics, and the astonishing mathematical coincidences we've already explored, lend it a powerful allure. It asks us to reconsider not just what the universe is, but how it began, inviting us to see the Big Bang not as a creation from nothing, but as a grand physical transition, a cosmic bounce, a seed sprouting in the fertile darkness of a black hole. It transforms the most violent, destructive forces in the cosmos into the ultimate act of creation, a testament to the boundless ingenuity of the universe itself. This radical idea, this cosmic bounce that transforms destruction into genesis, invites us to gaze upon the universe with new eyes. It's a perspective that suggests the Big Bang wasn't a singular, inexplicable event, but rather a recurring phenomenon, a cosmic echo reverberating through an unseen vaster reality. If our universe truly sprouted from the heart of a black hole, then the implications reach far beyond just understanding our origins. They suggest a profound, almost biological story of cosmic reproduction and evolution. Welcome to the Galactic Orchard, where we explore the mind-bending consequences of this universe within a black hole hypothesis. Imagine, if you will, physics not just as a set of static laws, but as a dynamic, living force, a form of cosmic genetics. In this grand orchard, universes are not isolated entities, but rather the fruit of parent cosmoses, each one carrying the genetic code of its progenitor, ready to seed the next generation. Think about it. Our universe is governed by a precise set of fundamental constants: the speed of light, the strength of gravity, the mass of an electron, the fundamental charge. If these constants were even slightly different, our universe as we know it simply wouldn't exist. This is the enigma of cosmic fine-tuning, a puzzle that has long perplexed physicists and philosophers alike. Why are these values so perfectly calibrated to allow for complexity, for consciousness, for us? This is where the idea of cosmological natural selection, a concept championed by theoretical physicist Lee Smolin, enters the stage, offering a startling, elegant answer. In Smolin's vision, our universe is not just a random occurrence, a lucky throw of the cosmic dice. Instead, it's the product of an evolutionary process operating on a scale so vast, it almost defies comprehension. If universes can give birth to other universes through black holes, then the fundamental constants of a parent universe are, in a sense, passed down to its offspring. They become the genetic code for the new cosmos. Let's extend our orchard metaphor. A parent universe, like a cosmic tree, produces black holes, its seeds. Each black hole, in this incredible hypothesis, contains the potential for a new universe to sprout within its core. The genetic code of this new universe, its fundamental constants, its basic physical laws, would be closely related to those of its parent. But perhaps, just like biological reproduction, there are slight variations, cosmic mutations, in each new generation. Now, consider the fitness of a universe in this cosmic evolutionary game. What makes a universe successful? In this model, success is measured by its ability to reproduce, to create more offspring universes. And how does a universe create offspring? By forming black holes. Therefore, universes with physical laws that are particularly good at creating black holes would be more reproductively successful. They would create more seeds, more offspring, and thus, their particular set of fundamental constants would become more prevalent throughout the multiverse. Visualize this. A universe with physical laws that are, say, too weak for stars to form, or too strong for matter to coalesce into galaxies, would produce very few, if any, black holes. It would be a barren tree in our galactic orchard, producing no fruit, no seeds. Its lineage would quickly die out. But a universe like ours, with its seemingly fine-tuned constants that allow for the formation of massive stars, and subsequently countless black holes, billions upon billions of them, would be incredibly prolific. It would be a mighty, fertile tree, constantly sowing the seeds of new cosmoses. This concept flips the idea of fine-tuning on its head. Instead of asking why our universe is so perfect for us, we might ask, is our universe perfect for reproduction? The realization dawns that our universe's seemingly benevolent laws might simply be the most efficient way to generate the next generation of universes. The intricate dance of gravity and matter that forms a galaxy, then a star, then a black hole. It's all part of a grand evolutionary strategy. It's an aha moment that transforms our understanding of cosmic purpose. But this model doesn't just offer a solution to the fine-tuning problem. It also provides a profound answer to one of the most perplexing paradoxes in all of physics, the black hole information paradox. For decades, physicists, led by Stephen Hawking, grappled with a deeply unsettling question. What happens to the information of everything that falls into a black hole? According to quantum mechanics, information, the unique configuration of particles, their properties, their quantum states, can never be truly destroyed. It can be scrambled, transformed, hidden, but never utterly obliterated. Yet, when matter falls into a black hole, it seems to vanish without a trace, its identity apparently lost forever. A black hole, characterized only by its mass, charge, and spin, appears to be a cosmic eraser, wiping out the rich tapestry of information that once described the matter it consumed. This contradiction between general relativity, which suggests information is lost, and quantum mechanics, which says it's preserved, has been a thorn in the side of theoretical physics for half a century. However, if a black hole is not an endpoint but a gateway, if it's the seed for a new universe, then the information paradox finds an astonishing resolution. The information isn't destroyed, it's transformed. It doesn't disappear. It becomes the genetic code for the new universe unfolding within. The vast amount of information isn't lost to the void. Instead, it's encoded onto the event horizon, the two-dimensional boundary of the black hole, much like a cosmic holographic plate. And from this encoded information, a new three-dimensional universe emerges on the other side. This concept beautifully weaves in the holographic principle. Think of it like a cosmic cinema screen. Everything you see in the seemingly 3D movie is actually projected from a 2D surface. The information that describes our universe could be the encoded legacy of a parent universe. This means that the genetic code for our own universe might be a direct inheritance from a previous cosmic generation. The information paradox isn't a paradox at all. It's a profound mechanism of cosmic reproduction. This perspective shifts our understanding of black holes from mere devourers of light and matter to cosmic midwives, birthing new realities. Physics, in this grand scheme, is not just about describing what is, but about understanding the biological processes of the cosmos. The implications are staggering. Our universe is not an anomaly. It's a living, breathing part of a vast, interconnected family of cosmoses, an infinitely branching lineage. This isn't just a multiverse theory. It's a fecund multiverse, one teeming with new births, constantly evolving, constantly adapting. It redefines our place in existence, our very existence. The intricate complexity of life on Earth might be an unforeseen yet beautiful side effect of the universe's ultimate drive to propagate itself. The stars we gaze upon are not just distant lights. They are the very engines of this cosmic evolution, the factories of future universes. Of course, this remains a highly speculative hypothesis, a fascinating possibility at the fringes of theoretical physics. The evidence is primarily theoretical and computational, not observational in the traditional sense. We cannot yet peer outside our universe to confirm the existence of a parent cosmos, nor can we directly observe a baby universe being born from a black hole. Mainstream cosmology continues to explore other avenues. The concept of torsion is not universally accepted, and direct observational evidence for a parent universe remains by definition elusive. How could we ever look outside our own universe to confirm such a radical idea? Yet, the elegance of the solution lends it a powerful allure. It asks us to reconsider the Big Bang, not as a creation from nothing, but as a grand physical transition, a cosmic bounce, a seed sprouting in the fertile darkness of a black hole. It transforms the most violent, destructive forces in the cosmos into the ultimate act of creation. This journey has taken us to the very edge of human understanding. It's a testament to the power of curiosity, the relentless human drive to understand our origins and our place in the cosmos. But if our universe is truly a black hole inside another, what does this imply about the ultimate fate of our own universe? If we are a cosmic seed, what kind of fruit will we bear? What does our future hold if we, too, are destined to become a parent cosmos, scattering our own seeds into the vast, unknown orchard of the multiverse? If these questions ignite your cosmic curiosity, remember to subscribe to Celestial Enigmas. We're just getting started on this incredible journey to unravel the universe's deepest secrets. Thank you for exploring these profound mysteries with us. We've soared through cosmic realms, touched upon the elegance of Einstein's equations, and glimpsed a universe potentially born from the heart of a black hole. We've dared to imagine our entire cosmos as a cosmic seed, sprouting from a parent universe, carrying the echoes of its origin within its very fabric. The sheer audacity of the idea, the breathtaking mathematical symmetries, and the elegant solutions it offers to some of cosmology's deepest puzzles can be profoundly captivating. It's the kind of grand narrative that fuels our imagination and pushes the boundaries of what we think is possible. But here, at Celestial Enigmas, we know that truly understanding the universe isn't just about embracing beautiful ideas. It's also about subjecting them to the most rigorous scrutiny, holding them up to the cold light of skepticism, and asking the tough questions, because that, my friends, is the very heartbeat of science. It's the crucible where speculation is forged into theory, and theory, perhaps, into truth. It's a process demanding humility and an unwavering commitment to evidence, even when that evidence doesn't yet exist. So let's gather around a different kind of cosmic table now. Imagine with me a scientific roundtable, not of agreement, but of vibrant intellectual challenge, as we present the compelling hypothesis that our universe is a black hole within another. Watch as stylized avatars representing esteemed yet skeptical physicists, appear around us, ready to engage. They're here not to dismiss, but to dissect, not to destroy, but to demand. They represent the collective wisdom and cautious optimism of the scientific community, reminding us that extraordinary claims require extraordinary evidence. Their voices, a chorus of informed doubt, begin to emerge. The first to step forward, perhaps an avatar representing a grizzled veteran of cosmological research, would raise a fundamental point: the profound lack of direct observational evidence. We've meticulously explored the striking mathematical parallels between the Schwarzchild radius of a black hole and the Hubble radius of our observable universe. We marveled at how the estimated mass of our universe, roughly 1.5 x 10^53 kg, when plugged into the black hole equation, R^2 gmMCU, yields a radius of approximately 13.8 billion light-years, a figure that astonishingly matches our universe's age-derived radius. And we pondered the critical density, that incredibly low average density of 9.9 x 10^27 kg, about 6 protons per cubic meter, which our flat universe exhibits, and which, coincidentally, a black hole the size of our cosmos would also possess. These are indeed fascinating numerical coincidences, almost poetic in their alignment. But, as our skeptical avatar would gently yet firmly point out, a mathematical echo, however resonant, is not the same as a smoking gun. We are, by definition, inside this potential black hole. From our vantage point, the uniform expansion we observe, consistent with all our cosmological data, feels like a universe expanding into itself, not necessarily the interior of an external black hole. We haven't detected any definitive bruises or anomalies in the cosmic microwave background radiation, that ancient light from the early universe that could be unambiguously attributed to our universe bumping against the boundary of its parent, or to the specific gravitational signatures predicted by this model. While searches for such evidence are ongoing and incredibly exciting, nothing conclusive has yet emerged. What would it even look like to observe a parent universe from within our own? How would we distinguish the subtle imprint of an external cosmos from the inherent noise and complexities of our own universal evolution? The answers, for now, remain elusive. This hypothesis, for all its elegance, is based on inferential leaps and theoretical constructs, not direct, tangible observations. It's a testament to the power of our minds to conceive of such scenarios. But for science, the ultimate arbiter is always what we can actually measure and see. Next, a second avatar, perhaps representing a brilliant young theoretical physicist with a keen eye for foundational principles, would highlight the hypothesis's reliance on unproven modifications to Einstein's theories. Remember how we discussed the singularity problem? How both the heart of a black hole and the moment of the Big Bang traditionally posit an infinitely dense point, a place where the laws of physics break down. The universe as a black hole model, particularly as championed by physicists like Nikodem Popowski, offers an elegant escape from this. It suggests that instead of collapsing to an infinite point, matter falling into a black hole experiences a bounce due to exotic physics, perhaps related to spacetime torsion, as described by Einstein-Cartan theory, or quantum gravitational effects, like those explored in loop quantum gravity. This bounce then seeds a new expanding universe on the other side of the event horizon, effectively replacing a problematic singularity with a physical transition. However, the skeptical avatar would interject. These modifications to general relativity, while providing a beautiful solution, are themselves highly speculative. Einstein's general relativity has been rigorously tested and confirmed across an astonishing range of phenomena, from the bending of light by massive objects to the precise orbits of planets and the detection of gravitational waves. It is, in its standard form, an incredibly robust and successful theory. While we know it must eventually yield to a more complete theory of quantum gravity at extreme scales, we don't yet have that definitive theory. Theories like Einstein-Cartan or loop quantum gravity are compelling avenues of research, but they are not yet fully established or experimentally verified. To build a grand cosmological model on top of these unproven modifications means that the entire edifice stands on a foundation that is, itself, still under construction. The mainstream cosmological model, the lambda CDM model, while acknowledging its own limitations, such as the nature of dark matter and dark energy, largely operates within the framework of standard general relativity. Introducing new physics, while necessary for progress, requires a very high bar of evidence to be widely accepted. The beauty of a solution, our avatar would remind us, does not inherently guarantee its truth. A third avatar, perhaps a sharp statistician or a philosopher of science, would then weigh in on the nature of the evidence itself. The striking numerical coincidences, the matching Schwarzchild radius, the critical density, are indeed thought-provoking. But how much weight can we truly assign to them? Is it possible, they would ask, that these are simply profound mathematical coincidences, devoid of deeper physical meaning? After all, the universe is vast, and the equations describing its fundamental forces are complex. In the infinite tapestry of cosmic numbers and physical laws, might there not be many such coincidences that, while intriguing, do not point to a causal connection? Consider, for example, the universe's observed flatness. While the universe as a black hole hypothesis explains this by linking it to the critical density within the parent black hole, mainstream cosmology offers another, more widely accepted explanation: cosmic inflation. Inflation theory proposes a period of extremely rapid expansion in the very early universe, which would have smoothed out any initial curvature, making our observable universe of inflation. Also elegantly solves other cosmological puzzles, such as the horizon problem and the magnetic monopole problem, with fewer ad hoc assumptions than some modified gravity theories. While inflation itself has its own theoretical challenges and its precise mechanism remains unknown, its ability to explain multiple observations within the framework of standard GR makes it a more parsimonious, and thus currently preferred, explanation for the universe's flatness. The existence of an alternative, well-developed explanation for the same phenomena means that the mathematical parallels, while captivating, are not necessarily unique or definitive proof of a black hole genesis. The universe, in its grand complexity, often allows for multiple interpretations of its data, and discerning the true path requires an accumulation of overwhelming evidence. Finally, another skeptical voice might emerge, perhaps a quantum information theorist, to revisit the black hole information paradox. We touched upon how this model offers a potential solution. Information isn't destroyed. It's effectively the genetic code for the new universe inside. The information that seemingly vanishes beyond the event horizon of a black hole in the parent cosmos isn't lost from existence. It's preserved and processed into the initial conditions of the new offspring universe. This is a truly mind-bending proposal, offering a tantalizing resolution to one of physics' most enduring puzzles. However, our quantum theorist would caution, the very nature of this solution is itself deeply theoretical and introduces new layers of complexity. While it provides a conceptual framework for information preservation, the precise mechanism by which this genetic code is transferred and imprinted upon a new universe is far from understood. It requires specific and, as yet unverified, Physics at the quantum gravity scale. Does this solution truly resolve the paradox, or merely shift its location to another, even more abstract, realm of unproven physics? The information paradox is a battleground for some of the greatest minds in physics, and while the universe as a black hole model offers an elegant conceptual escape, its practical implementation within a fully consistent quantum gravity theory remains a formidable challenge. The skepticism here isn't about rejecting the idea outright, but about demanding the intricate, mathematical, and ultimately testable details of how such a process would actually unfold. So, here we stand, at this intellectual roundtable, bathed in the glow of both brilliant speculation and rigorous skepticism. The universe as a black hole hypothesis, with its profound implications and elegant mathematical underpinnings, has faced a course of challenging questions. It lacks direct observational evidence. It often relies on modified theories of gravity that are themselves unproven. Its compelling mathematical coincidences might just be that, coincidences, with alternative, more established explanations available for phenomena like our universe's flatness. And while it offers a solution to the information paradox, that solution introduces its own set of theoretical hurdles. But this, my friends, is not a defeat. This is not a dismissal. This is, in fact, the very essence of how science progresses. This is our aha moment in understanding the scientific process itself. Even if a beautiful idea, like our universe being a black hole, ultimately proves to be incorrect, the intellectual journey of exploring its limits teaches us more about the universe than we could have ever imagined. The act of questioning, of seeking evidence, of demanding rigor, is not a barrier to knowledge, but its most powerful engine. When we consider the critiques of this hypothesis, we gain a deeper appreciation for the strengths of general relativity and the established lambda CDM model. We learn about the challenges of quantum gravity and the immense difficulty of peering beyond the observable horizon of our own cosmos. We're reminded that the universe doesn't owe us simple answers, and often the most profound insights come from the struggle to reconcile conflicting ideas and incomplete data. It's the relentless testing, the constant refinement, the willingness to be proven wrong that pushes the boundaries of human knowledge. The avatars around our virtual table begin to fade, not in triumph, but in thoughtful contemplation. Their skepticism wasn't a verdict, but an invitation to dig deeper, to search for new evidence, to refine our theories, or to perhaps one day formulate an entirely different, equally audacious idea that stands up to even greater scrutiny. It's the questioning, not just the answering, that truly matters in this grand cosmic quest. For every profound question we dare to ask about our universe, even the ones that lead us down speculative paths, we ultimately learn more about the scientific method, about the limits of our current understanding, and about the boundless potential for future discovery. What new evidence, then, might one day emerge that could either bolster or completely unravel this captivating black hole universe hypothesis? What observations could possibly tip the scales in this grand cosmic debate? And so, we stand at the precipice of a truly audacious idea, one born from the very same equations that describe the dance of galaxies and the fabric of reality itself. We've explored the mathematical whispers, the surprising coincidences that suggest our universe isn't merely like a black hole, but that it is the interior of one, gestating within a grander parent cosmos. But what does it truly mean to live inside a cosmic seed? What does this perspective reveal about our story, our place, our brief, shimmering existence within such an incomprehensible framework? Imagine for a moment, if you will, that this hypothesis holds true. You are an inhabitant of this cosmic seed, much like a tiny sprout unfurling within the dark, rich soil of a larger world. From your vantage point, everything would appear exactly as it does now. The stars would twinkle, the galaxies would swirl, and the universe would continue its majestic, accelerating expansion. You would not feel the crushing gravity one might intuitively associate with a black hole. Why? Because the gravitational forces within such a structure would be uniformly distributed across the immense scale of our cosmos. The event horizon of our parent black hole wouldn't be a wall you could see or touch. It would be the very edge of our observable universe, the boundary beyond which light from the parent cosmos can never reach us. It's a horizon of information, not of physical restraint, in the way you might imagine a tight, inescapable box. This perspective, while mind-bending, offers elegant solutions to some of cosmology's most enduring mysteries, the very puzzles that have haunted scientists since the dawn of cosmic inquiry. Perhaps the most profound of these is the issue of the Big Bang singularity. But what if, instead of an unknowable singularity, the Big Bang was a cosmic bounce? What if the matter and energy of a collapsing star in a parent universe, instead of reaching infinite density, reached a critical point where quantum gravitational effects became dominant, preventing collapse to a singularity, and instead causing a rebound, a colossal re-expansion into a new infant universe, our universe? This is precisely what physicists like Nikodem Popowski propose with their models, suggesting that the torsion or twist of spacetime itself, a feature often overlooked in simpler models of gravity, could provide the necessary repulsion to prevent a singularity and instead facilitate this cosmic rebirth. Our Big Bang, then, wasn't a sudden, inexplicable genesis from nothing, but a smooth physical transition from a prior state, a profound act of cosmic recycling. Now, let's revisit the stunning mathematical mirror we observed between the properties of a black hole and our own universe. Remember the Schwarzchild radius, the gravitational event horizon of a black hole, defined by a simple, elegant equation, r star 2g tahuhusu. The almost uncanny coincidence is that if you take the estimated mass of our observable universe, an astronomical 1.5 x 10^53 kilograms, and plug it into the Schwarzchild equation, the resulting radius is, astonishingly, also approximately 13.8 billion light-years. Furthermore, consider the critical density of our universe, the precise average density required for its geometry to be flat, neither curving inwards nor outwards. This incredibly low density, roughly equivalent to just 6 protons per cubic meter, is exactly the average density a black hole, the size of our observable universe, would possess. These aren't just minor similarities. They are profound mathematical echoes, suggesting a deep underlying connection. These are the whispers of evidence that fuel this extraordinary hypothesis, evidence found not in telescopes, but in the elegant language of mathematics itself, hinting at a reality far grander than we've yet conceived. If our universe is indeed a black hole nested within another, it also offers a compelling perspective on the black hole, the information paradox. When something falls into a black hole, is the information contained within it, its quantum state, its very essence, lost forever? This question has plagued physicists for decades, but if, as this theory suggests, the interior of a black hole is a conduit to a new universe, then perhaps the information isn't destroyed, it's simply transformed, becoming the genetic code for the new cosmos. From the perspective of a being in the parent universe, falling into a black hole is a one-way trip, an irreversible journey. And from our perspective, inside the child universe, time moves inexorably forward, suggesting that our universe's fundamental arrow of time could be a direct consequence of the one-way nature of the black hole event in the parent cosmos. If universes can give birth to other universes through black holes, then there might be a form of cosmic natural selection at play. As theoretical physicist Lee Smolin has proposed, universes with fundamental constants and laws of physics that are conducive to producing more black holes would, over aeons, out-reproduce those that don't. And the echoes don't stop there. This hypothesis resonates with another profound concept in physics, the holographic principle. This idea suggests that all the information contained within a three-dimensional volume of space can be encoded on its two-dimensional boundary, much like a hologram. Think back to the earliest civilizations, when the Earth was believed to be the unmoving center of all creation, with the sun, moon, and stars revolving around it. This geocentric view was not merely scientific, it was deeply theological, placing humanity at the pinnacle of cosmic significance. Then came the Copernican revolution, a radical shift that dethroned Earth and placed the sun at the center of our solar system. This was a profound and unsettling revelation, forcing humanity to acknowledge that our home planet was just one of many worlds orbiting a star, no more special than its celestial neighbors. Centuries later, as telescopes grew more powerful, we realized that our sun was just one of billions of stars, nestled within a vast spiral arm of the Milky Way galaxy. Our sun, once the majestic centerpiece, became a speck of light in an unimaginable cosmic island. And then, the 20th century delivered another humbling blow. Edwin Hubble's observations revealed that the Milky Way was not the only galaxy. It was just one of billions, scattered across an ever-expanding cosmic ocean. Our galaxy, once thought to be the entirety of the universe, was reduced to a single grain of sand on an infinite beach. Now, we stand at the threshold of perhaps the most humbling and yet most magnificent re-evaluation of all. This black hole universe hypothesis suggests that our entire cosmos, with its billions of galaxies, its unfathomable distances, its very fabric of spacetime, might itself be just one single cell, one cosmic seed, one brief flicker of existence, nested within an unimaginably vaster parent cosmos. It challenges our intuitive sense of scale, our deeply ingrained desire for cosmic significance. It asks us to consider that perhaps our universe isn't the entire story, but just one chapter in an infinitely unfolding cosmic saga. If our entire existence is but a single atom in a far grander cosmic organism, does that diminish us, or does it grant us a breathtaking, beautiful, and eternal place in the ultimate story of cosmic birth and rebirth? This is the kind of profound question that drives us, the kind that celestial Enigmas loves to explore. If you've found yourself captivated by these cosmic mysteries, if your mind has been stretched by the sheer audacity of these ideas, then you're exactly where you're meant to be. Join our growing community of cosmic explorers by hitting that subscribe button. Let's continue to journey together into the unknown, because the universe, in all its perplexing glory, is always waiting to reveal another one of its breathtaking secrets.